GeoEstima Podcast, Season 2, Chapter 5. Hi, in the first chapters of this season, we talked about the sampling process and then about its quality control. Now we will continue with implicit geological modeling and its differences from explicit geological modeling, so we can keep discussing and learning more about the geo-mining-metallurgical business in Chile and the world. To start, creating a three-dimensional geological model of a deposit is a fundamental activity in the mining industry because it provides key information for evaluating exploration potential, geotechnics, hydrogeology, and mineral resources. These, in turn, are the basis for estimating mineral reserves and assessing the economic feasibility of a project. A geological model is composed of several elements, such as lithology units, alteration zones, mineralized zones, mineralogical speciation, dikes, veins, structures, structural blocks, and others. All this is spatially represented as three-dimensional geometric objects, that is, solids and surface that have the particularity of being attributed temporally. For constructing a three-dimensional geological model, two methodologies are currently available. The first is explicit modeling, which involves directly constructing three-dimensional models. For this, detailed and specific geological information is used by drawing on two-dimension projections, that is, on well-known sections and plans, either manually or digitally. The solids or surface are obtained by triangulating from these sections and plans or through orthogonal projections or extrusion of the two-dimensional polygons in the block model. For this reason, this technique has also been called pseudo-three-dimensional, and it was the classic geological modeling done in the 1980s and the 1990s on paper and later digitalized with CAD tools in various mining software since the 1990s. The second methodology is implicit modeling, which is a computational technique that allows generating surface and solids directly from geological data through algorithmic interpolations. This disruptive technique broke into the mining industry in the mid-2000s and changed the rules of the game for three major reasons. It eliminated the need for sections and plans, significantly reduced modeling times, and finally allowed geologists to obtain more than one version of a model from the same data. Let's go step by step. What is implicit data? The input data of geological model includes all the geological information captured by geologists in the field and laboratory. Primarily, data from drill samples, surface geological maps, or underground workings are used. Geophysical, geochemical, hydrogeological, geotechnical, and other records can also be added. Essentially, any data expressed as points or lines in space. In general, geological data is categorically. For example, if during drilling we record lithology, we register from the beginning to the end of the borehole. The types of rock, which may change at specific points, we call contacts between two lithological units. By recording the spatial trajectory of the drill holes through color coordinates measurements and trajectory readings of the boreholes, we can determine with high precision the spatial location of each segment of the borehole, particularly the coordinates of the contact points. Geometrically, contacts are expressed as points. In an explicit model, a contact only indicates the points where we switch from the one category A to another category B. Now, we can express this categorical data differently. Imagine we attribute or assign numerical values to each point or segment of the borehole. In the case of implicit data, this corresponds to the distance from the contact point between two categorical units. Thus, by convention, we assign the exact contact point a value of 0 and then assign distance values as we move away from this 0 point following the borehole trajectory. These distance values relative to the contact point are positive if we enter the geological unit being modeled or negative if we exit it. This transformation allows us to convert the original categorical data into continuous numerical values, each spatially located. Since we have transformed categorical data into continuous data, it becomes possible to use spatial interpolation algorithms such as kriging or other radial basis functions, known as RBF. It is important to understand the spatial interpolation involves estimating values at unsampled points in space based on samples from drill holes, channels, or surfaces. In this case, we will interpolate three-dimensional the distance to a geological contact to obtain within this space a distribution of values equal to 0 corresponding to the spatial location of several contact points between two geological units. After estimating the contact points in space, triangulations are generated using algorithms that connect these contact points, providing the solids or surfaces needed to construct the model. With the aforementioned methodology, we obtain multiple solids and surfaces that are later cut using Boolean operations. For example, computational operations that enable unions and intersections of three-dimensional bodies following geological temporality. This means younger surfaces or solids will cut or truncate older surfaces or solids. This final process allows us to obtain the three-dimensional representation of our model, composed of surfaces and solids that spatially represent different geological units. Implicit modeling enables testing various versions of our three-dimensional model by adjusting different parameters, adding constraints, or modifying the interpolation of control points or polylines. Additionally, it allows for an efficient representation of geological uncertainty by generating multiple plausible models that fit the same available data. Advantages and disadvantages. One of the main advantages of implicit modeling is the ease of handling large datasets, as it allows working efficiently in 3 dimensions. This is not the case with explicit modeling, where data is managed in 2 dimensions. Additionally, the creation of surfaces and solids is very fast and uses workflows that enable the automation of geological model creation and updates when new information is added, saving time and resources. Likewise, it facilitates the management of faults and folds, which is a complex task in explicit models because this must be projected abstractly between sections. Implicit modeling allows defining multiple structural trends and applying them as controls in the creation of solids. This iterative process makes it possible to test multiple hypotheses. Finally, the three-dimensional display of data makes it easier to infer and visualize complex geological structures in a way that explicit modeling cannot achieve. The disadvantages are that it requires the user to have an advanced understanding of the software, and sometimes this skill stands out more than experience in geology. It is crucial to ensure that databases are consistent and validated. Then, working with interpolation algorithms, new data, even from distant areas, can modify the solids and surface previously created in areas where no new information has been incorporated. As in any modeling process, this effect of information directly influences the quality of the model. In areas lacking data, the technique must resort to extrapolation, which does not always yield optimal results. In our professional experience, we have successfully created many complex models of various types of deposits using implicit modeling. We have modeled paleofluvial systems, models that include structural blocks ruptured along faults, mineralized systems associated with pull-apart structural arrangements, complex vein systems, stratified unfolded rocks, dike swarm zones, sequences of instructions, and more. However, this is not only due to advanced software expertise, but also to the knowledge and experience of the geological team in charge. Their input is critical in defining and conceptualizing the geology. Determining the chronological sequence of events, defining structural trends, adjusting various interpolation parameters, and finally, reviewing and validating the results. For this reason, I believe the key to success lies in the combination of geologists skilled in software and others with expertise in drilling, surface mapping, and drill core analysis. In other words, experience in rock recognition, fieldwork, and mine geology. Therefore, for a skilled and enthusiastic young professional, it is always advisable to seek guidance from more experienced colleagues. The future of implicit modeling. It is difficult to imagine a limit to the future of implicit modeling with new technologies, algorithms, and increased data capacities. Its functions will only expand over time. It is expected that the ability to handle and integrate large multidisciplinary datasets will improve the precision and quality of models. With technological advancements, higher spatial and temporal resolution could be achieved, which will be particularly useful for characterizing complex mineral deposits. Additionally, the integration of machine learning techniques could enable models to identify patterns from vast amounts of data, facilitating the prediction of the geometry and distribution of geological deposits. In fact, the use of machine learning is gradually becoming more widespread in the geomining industry. Moreover, there could be a deeper connection between implicit modeling and artificial intelligence, elevating automation and intelligent decision-making to a new level in the exploration and evaluation of mineral deposits. Finally, online platforms and collaborative tools may allow geologists and mining professionals to work together in real time on the development and refinement of implicit models, streamlining the process of deposit evaluation. In the next chapter, we will explore the final topic of this season, one that is particularly fascinating to me: reconciliation. We invite you to stay tuned for the next chapter, where we will continue discussing and learning more about the geomining metallurgical business in Chile and the world.